This presentation relates to a brief overview of work done. That's work done in the mechanical context by a force over a distance. Examples of work done on rigid bodies, in other words bodies that are not changing in shape, not deflecting. When we're draw filing in the workshop, we're applying a force over a distance, the force from the file over the distance of the metal. It's work being done. An automatic hacksaw, it's work being done by the teeth as they cut at the bar as they move from right to left. An old-fashioned shaping machine where the tool applies a force over a distance as it gouges the workpiece. All of those are work done in a linear context, but we can also have work done in an angular context. Here we've got a force applied to a handle, and that force multiplied by the distance travelled in a circular path will relate to the work done. Other illustrations, if we apply force to the handle of the hydraulic jack here, so this force F applied over some vertical distance up and down will produce work. If we want to raise a load vertically over a distance, again work is being done. So work done in the mechanical context is defined as force times the distance moved in the direction of the force by the object or the body. Here are further illustrations of work done on rigid bodies. The bulldozer pushing the gravel, old-fashioned sedan chair where work is done by raising first of all the sedan chair to a height, and then work can be considered done in the horizontal sense as the sedan chair is moved from left to right. Again, a force over a distance. Work is done when digging. We apply force to our shovel and the force over a distance is work done. On a merry-go-round, work is done in the vertical sense by raising the passenger up and down as the merry-go-round goes around. So again, we got work done in the vertical sense. And I'm sure you can think of many illustrations of your own where a force is being applied over a distance and thus work is being done in either a horizontal or a vertical context. So let's formally define work done, usually given a symbol W. We need to be careful in some questions because also weight will occur in the question, so we've got W for weight and W for work done. Just to be careful with our nomenclature in some cases. So work is done when energy is transferred to or from an object. The amount of energy transferred is the product of the force F and the distance moved S. But note the distance moved is in the direction of the force. Our basic formula for work done is simply W is equal to F multiplied by S. So in the diagram above we've got a force that's applied to a body and it moves it from left to right here. We assume that force is applied constantly over the distance S when working out the work done. Notice the units of force will be in newtons. The distance moved in the direction of the force will be in meters. So in the SI system, the unit of work is the Newton meter. You're probably aware that the unit of work is actually given a special name of joule, capital J, after the English physicist James Joule. So 1 joule is equivalent to 1 Newton meter, and the units are effectively interchangeable, but more often we use joules for energy. In mechanics, work is defined as a scalar property, so it has a magnitude, but it has no direction. In other words, we can't draw vector diagrams of work. That makes no sense. However, be careful, the sign of work is important. For example, if the component of the force in the direction of the motion is negative, then the work done is negative. In other words, it's removed from the system. And for example, this occurs when pushing a crate over a horizontal surface. A force is applied to the crate to move the crate in the horizontal direction. But as we know from previous lectures, there will be friction effects occurring of the crate in contact with the floor. and the friction effects oppose the relative motion, and so is taking work out of the system as the friction effects heat up the floor. So it's important to understand that work can be positive or negative. Here's a brief example. Undertaken force, example 1. We're asked to find the work done by a force of 0.6 kilonewtons as it moves a body a distance of 2,000 millimeters. Our solution is given to us here. Now, first of all, be careful. The force is given in the question is 0.6 kilonewtons, so I would always remove the prefix and write that as 600 newtons. The distance, notice symbol S, is stated as 2,000 millimeters in the question. I would convert that to meters. I always use meters in dynamics. But now we have all the information to calculate the work done. The work done, W, is simply the F multiplied by S, in this case 600 multiplied by 2. So the work done is 1200 joules or 1.2 kilojoules. Example 2 is an illustration of circular motion where work is done. An effort, that's a force, of 30 newtons is applied to the handle of the jack shown in the question. In other words, this effort here is where the force is applied. If the handle has a length or radius of 300 millimeters, shown here, and it makes 20 revolutions, we've got to determine the work done. Just note for reference, calculating circumference, I use the formula pi times diameter or 2 pi r. So here's the applied force of 30 newtons and its circular motion is shown in the dotted line here. That's 1 revolution. So in our solution, from the question, the applied force is 30 newtons. The radius of the handle, called this r here, is 300 millimeters. Again, write that into meters, 0.3 meters. So to calculate the distance travelled in 1 revolution, I've called that S1 here, that's 2 multiplied by pi multiplied by r. So 2 pi multiplied by 0.3 is 1.885 meters. We know from the question there are 20 revolutions to consider here, so 20 multiplied by the 1.885. The total distance travelled in those 20 revolutions by the effort is 37.7 meters. Finally, calculating the work done, that's simply the force from above multiplied by the total distance travelled. So that's the 30 newtons multiplied by the 37.7 meters. Our final answer for the work done is 1,131 joules. Exercise 2. We've got to calculate the work done when a mass is lifted vertically by a crane to a height of 5 meters and the force required to lift the mass is 1.2 kilonewtons. If you think you can attempt this question without further assistance, I'd encourage you to stop the presentation, attempt it now, but the full work solution is shown on the following slide. Okay, here's exercise 2. Got to calculate the work done. We're given in the question that the mass is lifted to a vertical height of 5 meters. It's in the correct unit shown here on my diagram. And then the force required to lift the mass is 1.2 kilonewtons. Notice I put that into newtons here, 1,200 newtons. So all we've got to do is calculate the work done. So that's W is equal to F multiplied by S. And that's simply, in this case, 1,200 multiplied by 5. So 6,000 joules or 6 kilojoules is the work done. Let's briefly consider power. Now, power is defined as energy transfer, in other words, work per unit time t, also termed the rate of doing work. For an object on which the work is done for time period t, and this results in a displacement s in that time, the expression for power, P, is shown in the box. So power is simply the work done divided by the time taken. We can generate another equation for power. If we consider work is force multiplied by distance, we can replace this top line of the first equation shown here with F multiplied by S. And what we can note is that the S divided by T here is actually velocity V. So an alternative equation for power could be written as the force multiplied by the velocity. Considering the units again, we know that work done is Newton meters or joules. We know that time would be in seconds in the SI system, and velocity is in meters per second. In the SI system, we always determine the units from the equation given. So consider the top equation here, power is equal to work divided by time. Work would be in joules, time would be in seconds. So the unit of power could be written as a joule per second. However, we give the joule per second a special name, and I'm sure you know a joule per second is a watt. So we measure power in terms of the watt. Again, note that power is a scalar property. Example 3. A load of 30 kilonewtons is raised through a height of 2.5 meters in 1 minute by an electrical hoist. We're asked to calculate the work done and the power required. So again, extracting information from the question, the force is 30 kilonewtons. I've written that as 30,000 newtons. The height raised, S, is 2.5 meters. And the time taken is 1 minute. Notice that's been converted to seconds, 60 seconds. So part 1, we're asked to find the work done. It's simply W is equal to F multiplied by S. So 30,000 multiplied by 2.5 is 75,000 joules, or 75,000 kilojoules. And in part 2, we're asked to find the power required. Well, power is work divided by time. So in this case, it's the 75,000 joules divided by 60 seconds. So 1,250 watts, or 1.25 kilowatts. I'm now very briefly going to take you through some exercises from our workbook, and that will lead us then into some questions which I will leave you to attempt at your own pace. Exercise 4, we're asked to calculate the work done when a force of 400 newtons pushes an object a distance of 50 meters in the same direction as the force. We're given that the time taken for this to occur is 40 seconds. We've got to determine the power required. The answers are shown in the bracket on the right hand side. If you think you can attempt this exercise without further assistance, I'd encourage you to stop the presentation and attempt it now. But the full solution is shown on the following slide. So extracting the information from the question and drawing a diagram, we have a force of 400 newtons, and that's constantly applied over a distance of 50 meters in a time of 40 seconds. So the first calculation, find the work done, W equals F times S. So in this case it's 400 multiplied by 50, so that's 20,000 joules or 20 kilojoules, shown in the answer here. Step 2, we have to find the power required, and I'm using the formula here of W divided by T because I'm given the time in the question. So 20,000 divided by 40 is a value of 500 watts, or, as the question states, 0.5 kilowatts. Exercise 5, we've got to calculate the work done when lifting a mass of 102 kilograms through a vertical height of 12,000 millimeters. There's a hint in the question here. Force is equal to mass times gravitational acceleration, and we're also given the gravitational acceleration. So what the hint is trying to say is to calculate the weight of the object here, because it's that weight is the force that's moved over the distance. Again, if you think you can solve exercise 5 without further assistance, please stop the presentation now and attempt exercise 5. The answer is shown in the brackets on the right hand side. But the full solution is shown on the following slide. Exercise 5. Here's our diagram of the information we've got given. We've got a mass of 102 kilograms that's being moved over a distance of 12,000 millimeters. Notice I put that into meters here. In this case, the force will actually be the weight of the object here. So the first thing I do is calculate the weight force shown here. Weight force is mass times gravitation acceleration. So 102 kilograms multiplied by 9.81. So roughly 1,000 newtons is the weight of the object, and that's assumed to be applied over the distance of 12 meters. So knowing the force, we can now calculate the work done is simply force times distance. And we find the work done is 12 kilojoules. The question states 12,000 newton meters. Exercise 6, we're asked to calculate now the power required when a piston applies a force of 6.5 kilonewtons over a distance of 450 millimeters in 15 seconds. Again, if you think you can attempt this question, I'd encourage you to stop the presentation and attempt it now, but the full solution is shown on the following slide. Exercise 6, here's the solution. We're given in the question that the force applied from the piston is 6,500 newtons. We know the distance travelled by the piston in the horizontal sense, it's 0.45 meters. We're also given in the question the time taken is 15 seconds. The first part of the question wants us to find the work done, and again, work done is force multiplied by distance. So in this case, that's 6,500 newtons multiplied by 0.45 meters. So 2,925 joules is the work done. But ultimately, the question wants us to find the power required. So power is the work divided by the time. So the 2,925 newton meters or joules is divided by the 15 seconds. So 195 watts is the power required in that case. Exercise 7. A car pulls a trailer with a force of 1.5 kilonewtons at a speed of 32.4 kilometers per hour. And that's along a level track. We've got to calculate A, the power required, and B, the work done in 6 minutes. Notice we have a hint in the question for conversions between kilometers an hour and meters per second. Again, if you think you can attempt the question without further assistance, I would encourage you to do so, but the answers are shown here in the brackets on the right hand side. So here's the solution to exercise 7. We're given in the question that the force applied to the trailer is 1.5 kilonewtons. I've written that as 1,500 newtons. And we know that the velocity given is 32.4 kilometers per hour, which I've converted to meters per second using this conversion here. And that gives me a value of 9 meters per second. From the question, the time taken is 6 minutes, and again, I've converted that into seconds by multiplying by 60. So 360 seconds is the time taken. So in part A, we're asked to find the power required. So power is equal to force multiplied by velocity. The force is 1,500 newtons, and we've worked out the velocity as being 9 meters per second, shown here. So that evaluates to 13.5 kilowatts, shown here. And then in part B, we're asked to find the work done in 6 minutes. So to find the work done, noting that power is equal to work divided by time, we transpose the equation so that work is equal to power multiplied by the time. Power from above is 13.5 times 10 to the 3 watts, and multiply that by the time, 360 seconds. So 4.86 megajoules is the work done. Exercise 8. An effort of 50 newtons is applied to the handle of the screw jack shown. Effort's applied here on the handle. If the handle is 15 centimeters long and makes 2.5 revolutions, we've got to determine the work done. This exercise is very similar to example 2 shown previously in the presentation. I would encourage you to review the solution for example 2 and apply it to exercise 8. It's very similar. The answer is given in the bracket here. The full work solution will be shown on the following slide. Here's exercise 8 solution. On the right hand side here I've shown a small diagram which is a plan view of the screw jack, so looking down from the top on the screw jack. We will see the 50 newtons applied at the end of the handle. So the 50 newtons is the effort applied here at the end of the handle looking on the side elevation. So we know what the applied force is, that's the effort of 50 newtons, and that force is assumed constant over the 2.5 revolutions. So first of all we can find the distance travelled s, that's 2.5 revolutions multiplied by 2 pi r, 2 pi r being the circumference of one revolution. So 2.356 metres is the total distance travelled by that 50 newton force. And so we can work out the work done, which is the force multiplied by the distance. So 50 multiplied by the 2.356. So 117.8 joules is the work done. I will leave you with an array of tutorial questions to attempt at your own pace. Here's question 1W through to 3W. Notice the answers are stated in the brackets on the right hand side of each of the questions. Question 4W through to 6W. Question 7W through to question 9W. Just note in question 9W there's a hint. We've got to work out the horizontal force applied to the car. So this horizontal force component, and to find F, the formula that's given to us is P multiplied by the cos of angle theta, where P in this case is a force, and that force is the 200 newtons shown here. Don't forget we define work done as the force multiplied by the distance, and the force in the direction of the distance travelled. Question 10W. Again, if you read the question, you'll need to work out the horizontal force applied. We're given in the question the force P applied is 600 newtons, so that's this force here. As I said, it's a horizontal component of that force we need to calculate to get the work done. Be careful with question 11. It says that the width is 75 millimeters of the belt, and we're given a safe working load, that's a force or a tension in the belt, which is 360 newtons per 25 millimeter width. I'll let you consider how to apply that information to calculate the work done. And finally, question 12W. A crate weighing 900 newtons has a coefficient of friction, mu, with the wooden horizontal floor of 0.4. If a constant horizontal force of 450 newtons is applied, and that moves the crate 300 centimeters, we've got to determine the work done by each of the forces acting on the crate, and hence the total work done on the crate. Notice the hint in the question. We covered this in a previous lecture. Friction force is equal to mu times n, that's the coefficient of friction multiplied by the normal force. So in this case, you're going to work out the work input to the system, which is the force applied to the crate over the distance it travels. But we've also got work taken out of the system by the frictional force, assumed constant at the bottom of the crate, its contact with the floor. And we can work out the frictional force by the equation given here. That will be a negative work, that will be work out of the system. So to find the net work done, it will be the input work minus the output work. The answers are given here in the bracket. 1350 joules, that's the input work. The output work due to the frictional force opposing the relative motion of the crate is negative 1080 joules. And the difference between those values is the net work done, and that's 270 joules. I'd encourage you to attempt that question at your own pace.